Hi, AP Calculus students. This is the video for section 4.3 on Riemann sums and the definite integral. I'm doing this a little different today. Instead of at the whiteboard, there's so many notes for 4.3. It really brings section 4.1 and 4.2 together that I decided to actually write out the notes so that you can print them if you want, and to go over those notes using my writing tablet, since there's lots of pictures and lots of properties. So let's give this a try. There will be two videos, by the way. The first one will be on basic notes for 4.3, and then the second video will be the 4.3 examples. All right. Okay, so I pulled out the notes that I put in for section 4.3 in Schoology. Again, it's quite a bit, and so I hope that you are able to print them. If not, maybe you enjoy taking the time to write out notes. So here we go. An integral, here's number one, an integral shows geometrically as an area between the function and the x-axis. So we've talked about that a few times now in Riemann sums and in section 4.2. Okay, a definite integral. So right here, a definite integral means a definite area then. So we will have no plus c. So you may be like, well, where does the plus c go then? So again, because there plus c indicates a family of functions, and what we'll have is an actual function determined on a certain interval that has a definite area and will produce a definite integral also. So we'll see that a few times. Now on number two, this looks pretty calculus-ish, pretty complicated. Again, on the AP exam, there is no summation notation, the Greek letter E here, and there is no indices, which they use I's with. But to actually explain how a Riemann sum is related to an integral is important. So, and the summation notation is included in that. So in section 4.1, we just simply did the antiderivative, we did the integral, right? And then in 4.2, we talked about how we can estimate area between a function and the x-axis using left, right, and midpoint Riemann sums, right? So the Riemann sums are just an estimate of an area, for instance, like the area you see here. So how do we get a definite area when we don't have a geometric formula? If you notice, the area I have here is not a shape that we have an area formula for. It's not a circle, rectangle, right? It's not a triangle, but we obviously produce parts that have, you know, curves to them like you see here. And it's important for us to know what those areas are exactly. So what is the connection between estimating areas under curves and the integrals and having the exact integral in the exact area? Well, of course, it's limits, right? Limits is what connects our pre-calculus or our algebra and turns it into calculus. So let's take a look here. So I had mentioned this when I did a chapter 4 introductory, but let's just take a look at the picture here. Let's say you have this interval, f of x here on a to b. Notice if I pick an x value in between a and b and just call it c of 1, then this height up here would be f of c of 1, right? Notice also that if I pick an x, perhaps here or here, right, that the change in those x's we could call delta x, or, right, a change in x, the rate of change of x is also called the differential of x or the derivative of x. Okay, so f of x on a closed interval from a to b with delta x partitions. So just imagine that I just have two partitions, right? And I estimate the area of two rectangles just by dividing this area in half, right? The area, my estimate for my area probably wouldn't be that accurate, right? So what if I then did 4 rectangles, right? That area, since the heights would more closely match the function more often, that area and that integral might be more accurate. So, and as I add more and more rectangles. So as I add summation notation, more and more rectangles. So let's say I go from an I of 1 to n. So these would be the number of partitions, right? Maybe 2, then 4, then 100, then 1,000. So if I sum up the number of partitions of f of c of 1 of delta x. So notice that what I have here is a base, right? There's a base right here. And notice I have a height, right? So this is another good reason why here, when I integrate, I have the delta x or the differential of x. So this is a height times a base. This is the area of a rectangle. And I am adding up from 1 to n the number of rectangles. That would give me an estimate of the area or an estimate of the integral. Let's go a little farther then. Number 3, what is the connection then between Riemann sums and the integrals? And it would be a limit, of course. So the limit as the number of rectangles approaches infinity, right? Where here's the area and we're summing them up. Or we could say that's the limit as delta x approaches 0, right? Because then more rectangles that you have in a given area, right, then the smaller the bases become. The actual length of the base starts approaching 0. So the limit as delta x approaches 0 of this area of a rectangle added up will tend to give us the exact area, right? And that is the actual definition of what a definite integral is. We have, here's our integral. We have a lower xa, an upper xb. We have the base and the height of a rectangle. Again, another good reason why the dx is paired with the integral sign. And that is called the definition of a definite integral. It shows us as an actual area of the function on a to b between the x-axis. So just imagine how important that is now we can find the exact area using calculus of all types of areas that we do not have a geometric formula for. Isn't that cool? What we're going to do in section 4.3 though is relate the definite integral to an area using geometric formulas that we do know, just to help you get the hang of it. Okay. Now, because integrals are areas and because they are the inverses of derivatives, then we need to look at the rules now. So there's lots of rules for integrals, and I hope they make sense as I show them as areas to you. So A, the integral from A to A of f of x dx. So notice if your lower x is an A and your upper x is an A, then you have no base, right? You have no width. There's no distance between an A and a B. So when you try to draw the area, there's no area. So that's why anytime the lower limit and the upper limit are the same on an integral, that integral is 0 because there would be 0 area. Let's take a look at B. When you look at B here, right, we have the integral from A to B of f of x dx. And that shows what we're saying is that is equal to, I can break it up into 2 separate integrals or 2 separate areas, right? And so the integral, notice, let's take a look at this area, right? We can always now draw a picture of an area when you have an integral from A to C, right? Here's the base, right? A to C. And it's the area between this function and the x-axis, right? So here's this area here. So now if I add to it the area from C to B, oh, made a mistake in my notes, the lower, as you go left to right, the lower limit is obviously a C and the upper limit is a B, right? I have to see the connection here, right? Goes from upper to lower, and that allows me to go from A to B. Poopers, sorry about that. Anyway, if I drew this area from C to B between the function and the x-axis, right, here it is. So of course then, notice that I can just simply, the integral from A to B of f of x dx must be the entire area. So it's okay for me to add up those two integrals. All right, let's move down. So C, now what if the function f of x is less than g of x for any x on A to B? So I drew a picture of that. Here's f of x, and I made sure for any x on A to B that its output is less than g of x. Okay, then what this means is that the integral from A to B of f of x must be less than the integral of A to B of g of x, right? Because if I drew this area, here it is, right? And of course, if I drew this area, because g of x is above f of x, right? Here's the area all through here. Of course, this area under g of x is bigger than under f of x. So the integral of f of x is less than g of x. Now, did you know that area can be negative? It can. And I just want to explain real quick, even though I have plenty of notes, right? You can have a rate at which you gain money or lose money. And we know the integral of that is a position, a money position. How much money do you have? So if you have a rate at which you're gaining money, of course, you'll have a positive accumulation, which shows up as a positive area. If you are losing money, you have a rate that you're losing money, then of course your accumulation over time is you are losing money. You have negative accumulation, which will show as an area under the x-axis, okay? Let's take a look at D. Let's say you have the integral from A to B of f of x dx, right? I drew it, here's A to B, here's f of x, and here's the area here, right? Obviously a positive area, right? As you go from A to B, okay? Now, this equals, if you switch the upper and the lower values on the interval, then it will make this area negative. So again, if you switch the upper and lower intervals, it will switch the sign of the integral or the area. And here's why. Now we find that area can be negative. How? If f of x is a fixed rate at which you gain money, right? Notice over if x is time, this function outputs a positive value, a positive rate at which you're gaining money over A to B. Then if you go from B to A, if you say, hey, you know, it's A is now and B is a year from now. That's a Y, is a year from now. It doesn't want to write well for me. That's it. That's a year, is a year from now. In a year, you'll say, wow, I gained $1,000. If you start next year and go, wow, let me go back. How much less money did I have? Notice I said less money. You would have $1,000 less. You would actually lose money. You would lose area. And so this integral would be negative. On E, if f of x is greater than 0 on A to B, right? I made f of x above the x-axis. For every x, the output is positive. Then the integral from A to B of f of x of dx will be greater than 0, meaning it will be above the x-axis. It will be positive. If your function is less than 0, right, meaning for every x on A to B that it outputs a negative, right, on A to B, then the integral is less than 0, meaning that the area is below the x-axis and is considered negative. Okay, so we just saw another way an integral can be negative, other than switching, having a positive accumulation and going backward in time. If f of x is a rate of f of x for money, then the area between f of x and the x-axis represents accumulation of money. If f of x is a positive rate, you gain money. If f of x is a negative rate, then you will lose money. Okay, so this brings us to F. This is very, very important on the AP exam on F right here. Okay. When you integrate, let's say that f of x is not just above the x-axis and not just below the x-axis, right? But it's a little bit of both. Hold on here. I'm going to have to fix that. Hold on. This is going to take a sec. Okay. Okay. It's not just below the x-axis. Okay. There we go. Whoops. Sorry about that. What if the function is sometimes negative and sometimes positive on an interval from a to b? That means when you integrate from a to b, f of x dx, you will partially have a negative area where the function was below the x-axis, and you will partially have a positive area where the function was above the x-axis. And so when you add up these areas, because that's what an integral is, they'll have signs of opposite values and actually net out a position as far as a distance or money, right? And so that would be called your net gain, net loss, net area. All right. So if this is a rate, f of x, that you are walking, for instance, and you walk partially in a positive direction and then in a negative direction, it will give your net position where you land. Now, this is a very important word, total area. When you are asked for the total distance traveled, total money gained, that means that you will use the absolute value function. This comes up a lot on the AP exam, absolute value. Many, many students in the United States and in the world will not recognize that total means you need to put the absolute value on the function, but you will, and you will get that problem right. Okay, so when you have the integral from a to b of the absolute value of f of x dx, it will give you a total area. It will keep all positive areas positive, and it will make all negative areas positive, and it will add up the two areas that you see and give you a total accumulation, a total position, a total distance, not a net position, net amount of money. Okay. And in this picture then, the integral from a to b of f of x dx equals 0, right? But if you take the absolute value of the integral of a to b of the function dx, you will be adding up the two areas. Okay, here's my example. So I'm just going to say it instead of writing it. Example, Miss Culver's story of walking to the lake. Let's say we're standing in our classroom, as we will be soon. And I call walking to the lake, walking east, positive, because I love the water. And I call walking away from the lake, back to the school, negative. Okay. Notice if I start at the school and walk to the water and back to the school, my net position is 0. I landed in the same position I started with. However, did I go a total distance? Yes, I did. I did 1 lap to the lake and I did 1 lap back. I actually have a total distance of 2 laps. So that's the difference, okay? On G, if f of x is even, they'll have one of these problems on the AP exam. If f of x is an even function, so notice I tried to draw it as even, where it's symmetric on both sides of the y-axis, then the area or the integral from negative a to 0, right? It's this area right here, equals the area from 0 to a, right? Because the function is even on both sides of the y-axis, that makes the area the same on both sides of the y-axis. Now, if the function is odd, like this is pretty much the y equals cube function, then the area from a negative a to a that you see here of the function will be 0, right? Because we have a negative area here, a positive area here. Due to symmetry, they are the same area and they will net out to 0. Okay, so that is the end of our notes. And next, what we'll be doing in the notes is examples from the text. So thank you. And we will do video number 2.